So here's cofactors for real. So I really doubt that. I kind of started working through the 4x4 and realized that if he does that, that's just crazy. 4x4 is so, because you end up making 16 3x3 matrices for the cofactors. Well, okay, if actually you only need 4 3x3 matrices because you don't need all the cofactors to find the determinant. You just find whichever 4 that you want, but it's 4 3x3 matrices, and those 4 determinants of 3x3 matrices, and that's 12 2x2 determinants with a bunch of plus and minus signs that you got to keep straight. So I kind of doubt he'll do that because it's just like computationally really crazy. So, but 3x3s are not too bad, and here's kind of what we've got. So the first thing to keep in mind is that there's actually going to be some terminology that's thrown around, and it's good to know the difference. So there's a cofactor matrix. A cofactor matrix is essentially a matrix of special determinants that you have for any invertible matrix. So any square matrix that's not, that doesn't have any, okay, it's got to be full rank, essentially. So it's got to have a perfect row echelon form, identity form. You have to be able to work it into that form. But this is actually a method where you can check if it is invertible. If it's not invertible, this won't work, so there's no risk of putting a value to it when it doesn't have one, because you actually will have value. And if it's not an invertible matrix, you will just get 0. So if you get 0, check it, and if that's not a problem, that just means it's not full rank. You might also hear the terms adjugate or maybe even adjoint. Adjoint is more old-fashioned in terms of what we're talking about here. Nowadays, it applies to complex matrices of a certain form, which you will not discuss in this class. But they are important for other things, so I don't know if you'll need them for other classes. They come up in quantum mechanics a lot, but I don't know about like engineering-wise where they come up. But adjoint, you might hear it, but like in old textbooks they used to use it, but now they call it an adjugate matrix. And that's essentially the same as the cofactor matrix, it's just transposed. And the adjunct, or the, what am I calling it? Adjugate matrix is also, and I'll get to this in a little bit, but it's equal to the determinant times the inverse. And that becomes more clear as to why later on. Okay, second thing is that regardless of what dimension these are, you're going to have this form. Right? So plus, minus, plus. Next one starts on minus, plus, minus. Basically, you just flip the signs both ways, right? It's not like plus, minus, plus, minus, plus. You know, it's not like you're continuing on the row going down. It's just that it has to be symmetric. Okay, so you always want these to alternate in both ways, right? So dot, dot, dot. 4x4, 3x3, 5x5, anything. 2x2, 1x1, it doesn't... 1x1, yes, it's true, but it doesn't really. It's kind of a special case. Anyway, so when you're making the cofactor matrices, what you're essentially going to be doing, or a way to think about this, is a cofactor of an element. So let's say the cofactor of this element 1, 1 is everything that is not 1, 1. It's the furthest thing from being 1, 1. And this happens in 4x4, 3x3. So 1x1 is the intersection of blocking out a row and a column, right? It's row 1 and it's column 1. So you block out row 1 and column 1, and then that is going to be your cofactor determinant. Or that's your, so you find the determinant of that little one right there. So your 1, 1 determinant is going to be that, right? It's those bottom 4. Now we do the same thing. You can block these out and block these out here. So now we're on the second column and the first, I can't see that well, second column and the first row. So what we end up doing is we say, okay, well, you see where the intersection is? Everything that's not that is where we get that. okay? And it's also, this is where you get the row plus column, -1 to that power, right? Because -1 to an odd power is -1, -1 to an even power is 1. So that's where you get this alternating thing. That's where they have that thing in the, where they say like you have the element to the I plus jth power, or not the element, you have the -1 to the, people say -1 to the I plus j. And that's the I plus j referring to the coordinate, not really coordinate, but I guess the position in the matrix. But an easier way to do it is just think about it like this, right? It does the same thing. So basically we've got that here. Okay, and then so we move on to the next one. We see the same thing going on. So now this is this one in the little bottom corner right here. 2, 7, -4, -4, right? Now we move down one row. We've got our minus, plus, minus from there. So, and then, so now we're going to be covering up the middle row. So, right, the first one that we have is going to be, obviously we're covering up, this element is blacked out. So we've got 3, -2, -4, 8, right? I'm not going to beat this to death, but you can see all these right there. And then, so this is your cofactor matrix. That's not, I don't know what the notation really is. Honestly, they probably changed it up, but that's how I put it here. So that's your cofactor matrix. Now, if we transpose this, if we flipped this over the identity line, that would give you your adjugate matrix. That's useful to know because you can actually, if you go into Desmos, you will find that there isn't a way to, they don't have adjugate function here. But they do have the inverse, and they do have determinant. So if you multiply the determinant by the inverse, so you have your matrix here, you get the inverse, you multiply it by its determinant, and you transpose that whole thing, that can assure you that you're going to get your proper values, so you can check your work. And as you can see here, those are the same ones that showed up when we did this. And so that just comes from these determinants. So, plus, minus, plus, minus, plus, minus, plus, minus. And that's what really everything ends up, how it all ends up working. No matter what dimension you're in, if this were 4x4, you'd have 16 3x3 matrices to find your adjunct. Or not, to find your, I keep calling it adjunct. To get your cofactor matrix. So that's obviously just ridiculous. And if they made you do that, that would just be crazy. But yeah, so remember this though. This might be useful for checking yourself on Desmos. So anyway, so we've got our matrix right here. Now we're going to do something a little bit weird. And this is also kind of crazy how this works out. But we're going to do not regular matrix multiplication, but what you're going to do is you're going to multiply everything with its cofactor. This is why they're actually called cofactors, because this is shows kind of an embodiment of what linear transformations are. And it's also kind of remarkable that they preserve these types of symmetries. It actually has to do with like a lot deeper theory on, they're called affine transformations. Affine, AFFINE, has to do with transformations that preserve the they preserve parallel lines. And affine transformations have particular invariant values. And the determinant is an invariant value. Well, that's not super important right now, but it is kind of weird because you'll see it pop up right here. But so -1 times 76. I'm not going to do all this math here, but as you can see, when we did that math in here, that gives you the same value for all of them. And that's actually the determinant value. So what that means is you don't actually need to use all of the cofactors. You just need to find a cofactor of this and multiply it. Okay, so multiply this with its cofactor, this with its cofactor, and this with its cofactor, or this and this, or this, and this. What they might do is have a matrix with a bunch of zeros in it, you know, an invertible matrix, so not all zeros, but like an invertible matrix with a bunch of zeros, so that, and that's where with the 4x4 he might make it easier. So let's say you have a 4x4 and you have some sort of a matrix that's got like one of the rows is like only has a 1 in it or something, um, and then a bunch of zeros all over the place. Look for the way that will be fastest, because if you multiply a bunch of zeros in there, you don't have to worry about it really. So yeah, that's cofactors there. Yeah.